I've got a question for you here. We have a line of charge. We have a cylindrical Gaussian surface that surrounds our line of charge. And we want to know what the flux is through the two flat ends of the cylinder. But it is A. It is A. The reason why it's A is because if you look at what the electric field is doing here, it's radially away, right? And on the edge, those vectors are parallel with the surface. So there's no flux. There's no electric field going through the ends. There's no electric field going through the ends, then there is no flux. Now, what is the electric flux through the wall of the cylinder? Let me know what you think about that one. B. Excellent. B. And why is it B? Well, remember what's going on here. Your flux is your electric field times your area. Well, it's a surface integral, right? But the electric field, we know, is constant all along the surface. And if you look at this surface here, what is its area, right? Well, what you do is you take that cylinder and you roll it out so it becomes flat. And it has a length of 2 pi r, right? 2 pi r. That's the length of it. Now, the other dimension we already know is L, so that means the area is 2 pi RL. If you want to get the flux, then you multiply by E. That's it. Okay. With that being said, let's do it. Let's actually do it. Let's use Gauss's law to determine what the electric field is due to an infinite line of charge. Now, we've already done this, right? We have already done it. What we did is we looked at Coulomb's law for a finite line of charge, and then we got an expression for that, and then we let the line blow up to infinity. We made an approximation, and then we got our result. That's fine. It was a bit of work. Gauss's law can give you the same result, but it's much easier to do. So let's go through how that process is. Now, one thing I want to bring to your attention before I jump into this and all the other examples is look for the consistency in how we solve our problems. There is, in Gauss's law, a particular method you go through, and a lot of aspects are the same for every problem. So look for that consistency. All right, so we start with our, we start with our Gauss's law expression. The closed integral of E dot dA equals Q enclosed over epsilon naught. So the first thing we do is say, what kind of symmetry does the wire have, and what type of Gaussian surface shall I use to enclose some of the charge? You don't have to enclose everything. You can just enclose part of it and make a statement about, how, when it's much larger. So cylinders match the symmetry of a line. So the line goes right through the axis of the cylinder, and that means the left-hand side integral can now be broken up into 3 integrals because the Gaussian surface has 3 sides. It's got the left, the right, and the wall. Now, the quick check stuff that we just did, we can see that the left and the right integrals are 0 because there is no electric field that passes through those. So they get taken out. Now, for the third integral, we know the electric field is constant along the surface. You're the same distance from the wire there. And so again, symmetry argument, every single point has to have the same value. You can't have a different value if you're the same distance away. So you can't have, yeah. All right, and so we take E out of the integral, and then the integral just becomes what the surface area of the wall is, which we just worked out. It's 2 pi r L. So our Gauss's law now looks like this. E times 2 pi r L equals Q enclosed over epsilon naught. The other aspect of Gauss's law is to now deal with the Q enclosed. Okay, so we can't enclose all of the charge, right? Because this thing is infinite. So we're trying to figure out how much charge is in our cylinder. Well, we have to invoke our charge densities. Okay, gamma, sigma, or eta, however you like it, and then rho. So this is linear. So that means the amount of charge that is enclosed in the cylinder, I'm going to call Q. And lambda is going to be Q over L, where L is the length of the cylinder. So that would represent the linear charge density, not only of the entire rod, but it would also be the section that is, inside the cylinder. That's the beauty of densities, right? So Q enclosed is lambda times L. So I plug that in right here, clean it up. The L's drop out. And I divide by the 2 pi r, and I end up with this familiar expression down here, lambda over 2 pi r epsilon naught r hat. And that's it. We got it. Right? Now, just by the way, the r hat comes ultimately from the e up here. I didn't put in integrals. I didn't put a vector symbol, but they should have vector symbols on them. All right, so that's the result we got before, but it's much nicer. The left and right sides of, you can see in the picture here, the left and right sides of the cylinder, the electric field doesn't pass through it. In fact, the electric field is perpendicular to the normal vector, and so that cross product that you have for flux is 0. So, I mean, really the bottom line is, the concept is, if there's no electric field going through the sides, it's all parallel to it. Yeah, okay, great. Any other questions about this? That's a lot easier, huh? But here's the trade-off. The stuff before was more what we call a brute force method. We had an integral and we just forced it. We just, like I said, okay, let's make point charges, let's identify where there are, and we'll just do, Gauss's, Coulomb's law. Gauss's law is a little more sophisticated. Mathematics, as you can see, is pretty simple. However, the concept is much harder. To know how to get to the simple mathematics is not an easy task. Let's keep pushing on. I've got a lot of examples today. Basically, the rest of this is just examples, just lots of examples. I don't have many slides, actually, today. All right, so now remember the plane of charge? Oh, my goodness. What did we do there? We had to work out what the electric field is due to a ring on an axis. And then we said, well, let's make this a disk. And then we had another integral to do. And then we said, okay, let the disk blow up to infinity, and that is an infinite plane of charge. It's like, woo, that was a lot of work to get there. And you look at the final answer, right? And it was surface charge density. I use eta, but I think your book uses sigma. Sorry, I should be using sigma, to be honest. But eta's, back in the day, I used eta a lot. Eta over 2 pi epsilon naught. I mean, you look at that, and you look at all the work that it took to get there, and then you look at the answer, and it's so simple. And you think, I don't know, you really got to do all that work? You don't. Gauss's law is the new and improved what the 20-year-olds do for their problems. I'm still stuck in the Coulomb's law stuff. All right, let's do it. What's a plane? What kind of symmetry does a plane have? Well, it actually has two types of symmetries. It has cylindrical symmetry. And it also has what we call planar symmetry. So actually both apply here. And what we can do is we can use a Gaussian surface that is either a box or a cylinder. They both work, actually. They both work. I'm going to go with the cylinder just because, I don't know, I think people will get confused by the box. I don't know. If you see here, if you decide to use a box, a rectangular box, nothing is different about what we're going to do here. There's literally nothing different at all. In fact, there's nowhere in the math here can you even tell I'm using a cylinder, right? So anyway, here's Gauss's law. Start with that. I like to always deal with the left side first. So my cylinder has three surfaces. It has a wall, and it has two ends. Okay, now the opposite is true from the last one. The wall has no electric flux. Okay, we know that the electric field, due to symmetry, has to point radially outward. So nothing goes through that wall. So that's 0. Now on either sides of the wall, the flux is going to be the electric field, all right, times the area. But the electric field is constant. If we put our cylinder and the cylinder goes right in the middle, right? So, I mean, the plane goes right in the middle of the cylinder. So on either sides, we know we're going to have the same electric field. That's a constant, too. We know that along that surface, symmetry doesn't allow the values to be different, okay? So that means you can take the E out, okay? Now we have, those two integrals are identical to each other. So I'm going to have a 2E here. Because I'm just going to say, let's just do one integral and double it, because the two integrals on the side are the same. They're completely the same. By the way, when I graded your homework that you turned in that was due, it was the 31st one, the one that was due on the 9th, I think. There was a line of charge that was horizontal, and there was a positive and a negative part. And a lot of you did the positive part and then you doubled it to count for the negative. But you can't do that. You don't have that kind of symmetry because the negative is always closer to the point than the positive is. So that symmetry is broken and you can't double it. Anyway, just so you know. You should check out the solutions on my webpage. All right. So what is this area? Well, the area is just the area of the ends. Now, the ends are circles. Okay, fine, but I'm not even going to say that it's a circle. I'm just going to say it's A. It's just some area. Right? Just some area. And this is why this is not different. Yeah, and this is why it's not different than the box. I can just say the ends of the box, they're probably squares or something, right? You can make them squares. And then that's just an area. Just say area. And so then you got to ask yourself right here, this little circle right here. Okay. So this little circle in here, that's the Q enclosed. Inside my cylinder, you have to express what the Q enclosed is. And that's real easy, right? Because this is a surface charge density, which is the Q that's enclosed over whatever that area is. But it's the same area as the ends. So Q enclosed is just eta times the A. So I put eta A here. The A's drop out. And we end up with our familiar expression right here. Probably should add a little R hat on there. Being a little sloppy right now. I'm sorry. A little R hat on that. Okay. And there we go. That was simple, huh? Now, again, the idea here is that there's a lot of concept involved. It takes a long time. So there's a lot of work in both problems. One is a lot of mathematics. The other one's a lot of concept. And, of course, the concept is the nice stuff. The mathematics is, the kiddie class is, different time, not this time. All right. We've got the big kid class here. Okay. Any questions about this one? It's actually, so let me know if you have any questions, but I will tell you this. I remember the first time I saw this, I was like, this is so easy that I clearly have no idea what I'm doing. Like, I don't even understand why it's this easy. So, you might feel that way. Or you might feel like, no, this is actually easy. I don't know. Anyway, if you have a question, let me know. Okay. Let's check the chat. Yeah, right, exactly. So I could have said it was 2 pi r squared, right, for the two areas. But I didn't have to, because I would have had a 2 pi r anyway on the other side, 2 pi r squared anyway on the other side. That's why the box works too. If you do a box, then you say the box has an area that's, I don't know, like a square, right? S squared or whatever you want to call it. And the other side is S squared too. The idea is that the areas show up on both sides. And ultimately, it doesn't really matter. The size of your Gaussian cylinder here is irrelevant. It's just irrelevant. It doesn't matter how big or small you make it, which should make sense because that's the sort of a property. Oh, knew it. All right. Now this problem, we didn't do this one before. Because it was too hard with Gauss's law. With Coulomb's law. Too hard for the calculus that you know. Now, you can do it with the calculus that you don't know, but you don't know it yet. So, and it's not the level of, it's higher stuff. So, but Gauss's law says fret not, we got it covered. We don't need that hard stuff. So let's do it. I'm going to do 2 examples here. two examples is what the electric field is due to a solid sphere of charge. So we have lines, planes, now solids. We're going to do a sphere. And we're going to do two things. We want to know what it's like outside and inside. Because this has volume now. So we can be outside and inside. So let's look at this one as well. Outside. Now, it should be obvious here that our Gaussian surfaces should be spheres, right? Because the charge distribution is a sphere. Match the charge distribution, right? So we got spheres here. One sphere is outside of the charge. And that's a real easy one because we have our Gauss's law. It's the first statement. Always write down the first statement as the Gauss's law. The electric field all along the surface is constant, right? Equal distant, same electric field, so that comes out. And then this becomes the surface area of a sphere, 4 pi r squared. What's Q enclosed? It's just Q. It's just the whole thing. We are able to contain the entire charge in our Gaussian sphere, so it's just Q. And we end up with this expression here, which you've seen that before. It's a point charge. Okay, a solid sphere of charge has the exact same electric field as a point charge. The exact same one. The only thing you got to be aware of here is that R is the distance from the center of the sphere to the point of interest, not from the edge. A lot of people want to use the edge. And my advice to you is to not use the edge. You have to go from the center. It's always the case. Inside's a little tricky. Inside's different. In fact, the left side of Gauss's law will be entirely the same. Okay, if you're inside the sphere, same thing's got to apply. You have to have the electric field be the same all around because of symmetry. Okay, if the electric field is different on different points, then your charge distribution is not uniform, and the problems can't be done in the way you want to do it. So the left side's all the same. E 4 pi r squared. Simple. But now, when we want to enclose charge, we don't enclose all of the charge, only some of the charge. So now we have to develop our Q enclosed, which is down here. Q enclosed is going to be rho, which is our volume charge density, times the volume of the Gaussian sphere. So that's the definition of rho in this context. Charge over volume. So Q enclosed is rho times 4/3 pi r cubed. All right. Now, what is rho overall, though? Like, what is rho? Well, rho would be the total amount of charge, which I'm just going to call Q, over the entire volume of the sphere, which is 4/3 pi r cubed. And so I rearranged and I get this expression here. So now I'm going to put this over here. I'm going to put in my expression for rho, which is 3Q over 4 pi r cubed, capital R cubed, right? And then the Q enclosed is the 4/3 r cubed divided by 3, and then I have my epsilon naught. And a lot of things cancel, right? Some 4 pi's go away, some r goes away, and we end up with this expression down here, which is pretty interesting. Okay, let's see what's going on with this thing. The electric field inside the sphere is linear with distance. That's crazy, right? So if you're in the center, the electric field is 0. But as you start to move out, the electric field grows linearly, gets larger and larger and larger and larger until you get to the edge. Now, when you get to the edge, what's your value of little r? It's big R. So you plug in your big R here once you're on the edge, and guess what you get? You get the expression that's up here, with obviously big R being evaluated. And that's what's called a boundary condition. That's how a way you can check your answers. The electric field has to be continuous here. So that means when you evaluate both of these expressions at capital R, they have to match. If they don't match, something's not right. Anyway, so it's linear, but ultimately, if you look at unit-wise, it's an r over r cubed. So there's overall a distance squared dependence still here. Well, unit-wise, I'll say, right? But it's interesting because guess what? Right, point charges when it's one over r squared. And then we look at line charges, and they go as 1 over r. Then we get planes of charge, and it's constant. And now we have a three-dimensional charge, and it goes as a linear factor, right? And if we have a tesseract, then it goes as r squared. Probably. I don't really know. I have no idea. I don't even know what that would mean. Okay. Don't make any Avenger references. That movie's dumb. I don't see why the squared cancels out from the r. What? Where? What? Well, here, if you're talking about this, there's an r squared here, and there's an r cubed here. So there's an r squared that cancels out, and you're left with an r on top. Yeah? Okay, cool. Great. All right. Questions? Any questions? Anything unclear? All right. So, again, I talked to you in the beginning of the class here. Consistency. Right? I state Gauss's law. I create a Gaussian surface. I evaluate my integrations. Now, your integrations, your closed integral is going to break up into an integral for every side that you have. In every integral, it's either going to be 0, or you can take the e out of it, and you just do the surface area of that surface. That's always how it goes. Well, for this level of, Gauss's law. If you go to higher level stuff, then they're going to want you to actually do some interesting problems. And then the other side is Q enclosed. How do you express that, right? If it's linear, lambda, or eta, or rho, and it all goes this way. So you just have to be able to express for the Gaussian surface how much charge is actually inside there. So that's pretty nice. This is good stuff. Let's keep going, though. Let's just keep pushing on. I don't think I have another example now. Glad I remember my slides. All right, question for you here. A point charge Q is located a distance r from the center of a neutral metal sphere. The electric field at the center of the sphere is what? What is it? I see. That stuff's nasty. 0. 0? What? 0? What? No, who has the high C that's good? Del Taco's got a high C. Del Taco's got a high C that used to cause me some kind of like physical pain. It was very strange. It's a story. I don't have time to tell it. But, dude, Mario, wait, you're joking, Mario. Joking. You don't like Del Taco? Jeez. All right, well, we're not going to go there. We'll be civil. We'll be civil. Okay. Yeah, well, I mean, it takes some time to like build your immunity and your. It's like when you take little bits of poison, so you know what I mean. It's like that. Just start off with like a little burrito and work your way up, and eventually you'll be invincible. Okay. Anyway. Okay. What's going on? Because you're thinking here, like, okay, we've got a point charge. I know what the electric field due to a point charge is. But this is a metal sphere. It's not an empty space. What happens to this metal sphere? What's the word for it, people? There's a word for it. Polarized. You bet. It's polarized. So you got a bunch of negative built up here and a bunch of positive built up here. And what happens is it cancels out the electric field in there, right? So what's going on there? Well, we got some interesting things to talk about here. Inside of a conductor, your electric field is 0. Okay? 0. Now, why? Here's why. If you have a conductor that is charged, for example, like this one here is positively charged, that positive charge doesn't just hang out inside the conductor. It wants to spread out as much as it possibly can, right? Because the positive charges repel, and what they want to do is they want to move away as much as possible. If there was no conductor here, they all would just fly off in different directions, infinitely in different directions. But they're contained in the conductor. And so the best they could do is get on the edges. So they build up all along the edges. So then what you could do is you make a Gaussian surface, a weird Gaussian surface. It could be weird, but it matches the exact shape of your conductor, like this thing here. And what's Q enclosed? 0. So what's the electric field? 0. Okay, if Q enclosed is 0, the electric field is 0. It is. Now, let's talk about this from a different perspective, though. All right? So let's look at this example here. You could say, all right, well, let's say it's not 0, right? Let's say the electric field, like a lot of you are saying A, right? You're saying A, and you're like, okay, well, there's an electric field there. It's equal to that. What does that mean? Well, here's what that means. You have a conductor. You have electrons that, can move around. And if you put an electric field in the presence of an electron, it's going to travel in the opposite direction, right? So what happens is, as soon as the electric field gets established, you got a bunch of negative charges wanting to go this way. So your negatives build up here. And then what does that do? Well, it makes your positives go over here. You got a bunch of positives that build up here. That happens basically instantaneously. I mean, when I say instantaneously, I mean like less than a nanosecond. So like say we just have our neutral metal sphere here and then we just plop down the charge. Within like a nanosecond, what happens is the distribution happens. But what happens is as soon as enough charge builds up, the field from this charge out here is canceled with the field that is generated by the polarization. Okay, so everything inside here becomes electric field becomes 0. Because if it was not 0, if the electric field was not 0, then charge would continue to build up and build and build and build. I mean, if the electric field is always going to be a constant there, then charge is just going to build up and build up until, I don't know what, the universe explodes or something. But that's what happens here. You have this instantaneous polarization, which then cancels the field out to the point charge, and then the electric field inside is 0. Okay, so now the electric field inside of a conductor is 0, right? Are you going to remember that? Sort of. That here's the thing. There's a lot of ways that looks. No, Walter, don't say yes. The answer is probably maybe. That's the answer. Not yes. Because if I just tell you, if I just say to you, the electric field inside a conductor is what? You say 0. So, okay, fine. But I can package that question in other ways where it's equivalent to that. And that's really what the goal is here, is to make sure that you can take all the different ways we could package this equivalent statement so that you still tell me yes. Okay, until we get to a point in the class where the answer is actually no. But for right now, it's yes. Right now, it's yes. Okay. But it will be no later. But it's yes now. Okay, when is it no? When you have circuits. That's different. But that's not electrostatics anymore. Remember, this is electrostatics right now. When you have current flowing in a wire, well, everything's different now. All right. Now, what's going on with the surface? Well, again, we use some Gauss's law arguments here. The electric field at the surface has to be perpendicular to the surface. Has to. Because if it was not perpendicular to the surface, if there was a small component, say for example, we had an electric field vector that went up like this. You know, stop. My gosh. So say an electric field vector went in a little bit of an angle. Well, there'd be a perpendicular component, but there would be a sideways component, what we call tangential component. And that would cause charges to shift around on the surface. But charges can't be moving around. They're going to align themselves in such a way that the electric field is established to be perpendicular, and that is the optimal distribution of charge that you have on the surface. Okay. So on the surface, there, outside of it, there is an electric field, and it is perpendicular to the surface. What is its magnitude? Well, zoom in enough to this surface, right? Let's zoom in. Because here's the nice thing about these things is that densities, right, scale, right? You can have a huge object with a density, and then you can look at a little piece of it that has the same density. So what if we really zoom in on the side of this Gaussian surface? If you zoom in enough on any surface, it's going to look like an infinite plane of charge. So we're going to do our Gauss's law stuff like we did the infinite plane of charge. So the flux is going to be EA, but 1A, not 2A's. When we did that problem with the plane of charge, we had two sides. But one side of the Gaussian surface is in the conductor, and the field is 0. So you only have one side. The right end of the cylinder has flux. The walls don't, and the end inside the conductor doesn't. So your flux is just EA, your Q encloses whatever charge is in there, whatever it is, but when you divide by A, that turns into the eta. And so the electric field is simply this. It's eta over epsilon naught. That's very similar to the infinite plane of charge. The infinite plane of charge had a 2 on the bottom. And the reason why this doesn't have a 2 on the bottom is because we don't have two sides. We only have one side contributing to the field. So when you have conductors, inside the conductor, electric field 0. I'll say that again. I have a summary later. Wait, do I? I guess it's another slide. So anyway, going back, the electric field inside a conductor is 0. The electric field along the surface of the conductor is perpendicular, and it has a value of eta over epsilon naught. Now, we have a conductor here now that has a cavity. Okay, so imagine this is a three-dimensional object and it has a cavity on the inside. Okay. You can say, well, this charge, right, has to distribute itself along the surface. What about an inner surface? Is there an inner surface? Well, there can't be anything built up on the inner surface because, again, the electric field inside the conductor is 0. And since the electric field is 0 inside the conductor, there can't be any charge that sits in there. Okay? If I draw a little Gaussian surface inside the cavity, Q encloses 0. And then if I'm outside the cavity, the electric field in the conductor is 0. So the electric field is 0. We can't have any Q enclosed. So if you have a cavity inside your conductor, that won't accumulate any charge on it, assuming that it's truly a cavity. There's things in here that might be different. I'll show you an example of that. But the charge has to distribute itself as far away as possible, so it's not going to accumulate on the cavity at all. All right, so this concept here has a lot of applications to it, and you've probably heard of the term Faraday cage. It's usually used as a joke among people who think they're smart. So they make funny jokes about Faraday cages, but it's a process that's called screening. And what that is, as you see in the example here, say you had a parallel plate capacitor of some kind, and you put a conductor in there, a polarization happens, just like I showed you in that first example there. Anyway, all right. So, yeah, this is the shielded thing, and that, I mean that's true. So what happens is this. I mean, what people make the jokes about, like on campus. Okay, so I don't know if you remember that we have a campus. It's over on K and 30th. Um, no, everybody's tattoos are great. Don't get me wrong. You can do it. You could put I and then meters right here, and then the joke is your heart's like right there. So I, and then nothing, and then meters, and then you can show people it, and it has like double meaning to it. Whoa, right? That's like, whoa. Yeah, so we have a campus. We actually have a campus. It's over on 30th and K. So some of you may be new, or some of you may be from back pre-COVID days. And yeah, we do have a campus. And so on campus, there are these buildings we have. And the building that we normally are in is this enormous steel structure. It's just steel, everything's steel, with some people inside occasionally. And that's a Faraday cage. Because what happens is the cell phone signals, the electromagnetic fields, can't penetrate through because of screening. So, I know I'm in my office trying to use my phone, and I'm not on Wi-Fi. Just garbage. Doesn't work at all. So, anyway, but they use this in a lot of those situations. It's useful in a lot of things. For example, you can also use it to shield things. So a lot of things like hospitals or buildings that have very sensitive equipment, they do screen into not allow outside, interference and things. So now, what if something is inside the cavity? What if something is inside the cavity? Now it's different. Because if you want to create, so look, if I create a Gaussian surface inside the conductor, right? Oh my goodness, stop. Why does it do this? I have to learn this thing, and I have not learned it. Okay, so if I do it like that, that's my Gaussian. There's a Q enclosed, so there's an electric field. So if I were to circle, the cavity now, the electric field's still zero. But in order to make sure the electric field's zero, now the cavity does have to have charge on it. Because what happens is whatever charge is in that cavity, the same amount of charge has to appear on the inner wall of the conductor there to cancel out the charge and to ensure the electric field is zero. Okay, so if there are things inside of your cavity for the conductors, you do have to worry about the charge on there. Okay, so we'll do some examples of that so you see it. Question for you here: a positive 3 nanocoulomb charge is in a hollow cavity inside a large chunk of metal that is electrically neutral. The total charge on the exterior surface of the metal is what? What is the charge on the exterior surface of the metal? Because B would be correct. So what's going on here? Here's what's going on. Inside the cavity is a 3 nanocoulomb charge. Maybe. So what builds up here? Okay, negative here, negative. How much negative? Negative 3 nanocoulombs negative. Sounds weird. So, but if this is electrically neutral, if we pulled in negative 3 nanocoulombs, then what has to exist out here is a positive 3 nanocoulombs. So what happens is, in a way, that charge that's in here translates its way out to the outer surface. That's interesting. Now, if I circle the whole thing and say, what's Q enclosed now? 3 nanocoulombs still. But they distribute themselves. All right. All right, so Big Gregory's here. Okay. All right, so inside The conductors. We want to find the electric field of a conductor, okay, in electrostatic equilibrium. So what we know is this, that inside the conductor, electric field 0. Okay, that's it. If there's any excess charge, it's on the surface. The electric field points radially away. And if we need to figure out what that is right outside the surface, it's 8 over epsilon naught. If your conductor has a cavity and there's nothing in the cavity, there's nothing there. But if there's something is in the cavity, then the same amount of charge builds up on the inner wall with opposite sign. All right, so we have a infinitely wide, so it stretches out infinitely on either sides, right? A conductor parallel to and a distance d away from an infinitely wide plane of charge. So yeah, so we have this conductor here has a thickness to it, and then we have this this flat one here. Okay, so we want to know what the electric fields are in the different regions. Okay, so above. Well, let's do this. Well, first of all, let's do the easy stuff first. In the conductor, electric field 0 because it's a conductor. That's it. There's no work you got to do. Electric field's in the conductor 0, and that's the justification. You say E2 is 0. We're inside a conductor. Simple enough. Okay. Now, above here, okay, we're looking at a infinite plane of charge here. Okay. Now, there's effectively 3 infinite planes of charge here. We got the top layer that's positive, the bottom layer that's negative, and then we have underneath that, we have a plane of charge there. So the plane of charge creates the polarization, positive and negative there. And those fields have to cancel each other out to make sure that the electric field inside is 0. So we know that the electric field above the conductor is the same as it's underneath the conductor. So once we're outside of the conductor, it's like the conductor doesn't even exist. It's like it doesn't even exist. Because right outside the infinite plane of charge, we know what the electric field is. Eta over 2 epsilon naught. And that means when you go past the conductor, it has to be the same. Because the polarization here creates an equal field that cancels out. So that field is still there technically, but there's a second field now, and it cancels out. And so above it, it's got to be the same. Now, of course, below it, it's also the same. Got to put a negative there because now it points down. Okay, so just one more time here. We have a conductor that's infinitely wide, and we got an infinite plane of charge. Okay, the conductor is polarized, but in such a way that the electric fields of the two things cancel out and become 0. Okay, but that means the electric field really is continuous from that plane of charge. It's just there's a region where it gets canceled out by something. So anyway, any questions about that? Okay.
Real quick,
Yes.
can we also relate that to the whole idea when we were doing problems with like boxes and shapes where it would have to go in through one side and then the same amount would have to go out the other side for it to be 0?
Yeah, that kind of applies. That's kind of a similar idea. Yeah.
Okay.
That would work. Yeah. It's a very similar idea. Okay. I got 2 more examples, and then we're done. Okay. So what do we got going on here? Is this the first example? A hollow metal sphere has inner radius A and outer radius B, so it has a cavity. The hollow sphere has a charge of 2q. That's nice. Point charge has charge q and it sits at the center of the hollow sphere. We want to determine the electric fields in the 3 regions. Inside the cavity, inside the conductor, outside. And we want to figure out how much charge is on the inside surface of the hollow sphere. Easy. Let's do it. Easy. You're going to like this one. All right. Oh my gosh, what a terrible looking sphere. Looks like I got wrinkled up over the years. I made this slide a few years ago and it's just wrinkled up. It's terrible. All right, let's try that up. Well, I mean, if it's not clear. You know, it's you have a well. I can't draw. You know what it is? It's because I can't draw circles at all. That's okay. And then it's got this inner radius A, and then the point charge is right here. Okay, so this is all. This is a cavity here, and this all has got. This is just right. So we want to turn the electric field in the region. So the first one to do is very simple, right? Inside the conductor, 0. So in the conductor, electric field 0 because you're in a conductor. Simple enough. Now, what about when you're in the inner cavity? Well, that's very simple because that's just a point charge, right? You create a little sphere inside of the cavity here. It's a sphere, and what's your Q enclosed? It's just the charge, right? It's just the charge. So your electric field when you are inside the cavity is just an electric field due to that point charge, and that point charge is just Q. That's it. All right. Outside now. Okay, outside, we are drawing, right, a larger sphere. Okay? And so the Gauss's law part of that is, you know, every time you have spherical symmetry and you're using a sphere, you know what the left side is going to be of your Gauss's law. E times 4 pi r squared, surface area of the sphere. And then the other side is Q enclosed. Well, we're able to enclose all of our charge here. We did. So how much charge is in there? 3Q. That's it, 3Q. And so the electric field is just the electric field of a point charge of 3Q. Again, so simple, it just seems like something's not right about it, right? Now, they do ask another thing here. How much charge is on the inner surface of the hollow sphere? Okay, well, if you have a positive, a 1Q on the in the middle here, then you have a negative Q that builds up on the inner surface, and then the outer surface has to have a 3Q. Has to have a 3Q, because remember, overall, it's 2Q. So if a negative builds up on the inside, then you have to push another positive Q out to the edge. So what you have here is you have, on the very inner portion, you have a positive Q, inner surface a negative Q, outer surface a 3Q, and overall everything is 3Q. That's it. Everything's 3Q. It's a great problem. Let's look at our last one now. We have our shape here. I already have it drawn because I didn't draw it. But, what's the total charge on each surface? So what we do is we have this. We have a cylindrical shell. We have an outer radius and an inner radius. And inside of the cavity is not a point charge. It's another conductor. Okay, but that doesn't have a cavity in it. So we want to know what the total charge is on each surface. And the way we're going to go about doing that is by looking at the electric fields that are given to us and working backwards to figure out what the charges are. Okay, so now at this point, we already know what these answers are going to be, right? If it's spherical symmetry stuff, if these are spheres, we already know what our electric field is going to be. It's going to match a point charge. So 1 over 4 pi epsilon naught Q over R squared. Now, for the inner sphere's surface charge. Okay, so what's the electric field in the cavity? It's 15,000 nanocoulombs. So that's the electric field. It does point inward, so it must be a negative charge there. That equals 1 over 4 pi epsilon naught Q over, now this R is the distance from the center. It's not the size of the conductors. When you have this we have this expression for the electric field, that R is distance from the center. And so we're 8 centimeters away. And we're told that down here. So gotta use meters, okay? Gotta use meters, represent. So then solve for Q here, and you end up with a negative 11 nanocoulombs. That's on the inner surface. Well, guess what's on the inner shell surface? A positive 11 nanocoulombs. Has to be the same. All right, now let's do the outer surface. The outer surface has 15,000 nanocoulombs as well, but it points outward. The fact that it points outward tells us that overall we are working with positive charge here. Okay, so we do the exact same thing. 15,000 equals 1 over 4 pi epsilon naught q over our new distance. This electric field is evaluated at 17 centimeters from the center, so 0.17. Solve for q, we get a 48 nanocoulombs. So 11, okay, on the inside, negative 11 on the inner shell, and the outer part of the shell is 48. The shell has a net charge of 59 nanocoulombs, okay, because we had 11 on the inside and 48 on the outside. You should add that up. Overall, it's 59. So if we took that inner portion out, we'd be left with a 59 nanocoulomb charge spread out on the outside. All right? So the thing that's tricky about this is anything tricky. When I see people mess this up, it's because of one thing. They get their R's wrong. You know, R is always the point of interest where the electric field's being evaluated to the center of your distribution. First years, right? Okay, fantastic. Now,